This is not my best solution, but it is a solution that I am pretty happy that I came up with. Um, 31, 33, minimum array end. You are given two integers, n and x. You have to construct an array of positive integers, nums, of size n, where for every, what was it? Well, yeah, this is just, this is a complicated way of saying that it increases. Um, and then when you AND all of the numbers at the end, you get x. Return the minimum possible value of nums n minus 1. So get the last number in that increasing sequence, provided that you increase as little as possible. So the first thought that comes along here is x will be the first number, because you can't have a number that's smaller than x that includes all of the bits within x, because you need to have all the bits within x to AND it all at the end and get x. Okay, because ANDing, like if you have 1000 and then you're trying to get a smaller number, any smaller number is not going to include this one right here, which means that when you AND them all at the end, it's not going to include that, and it won't include all of x. So we start at x and build up from there. So my first thought was I just kind of did a brute force algorithm where essentially I just counted upwards, and I would see, hey, does this number, what was it? Starting from x, I just counted upwards. I said, hey, does this number and x equal x? And if so, just add it to the sequence, and then just go until you get the last number in the sequence. You don't actually have to track the sequence, but you track how many elements you would have added to the sequence, and then once you get the last one, you return that. And that works. It's just really slow. So we had to be more clever than that, which of course makes sense. Then I realized, so it's basically, the hints helped me out here. Each element of the array should be obtained by merging x and v, where v is 0, 1, 2, and so on. And to merge x with another number v, keep the set bit of x untouched, and for all the other bits, fill the set bits of v from right to left in order one by one. So that's the core of this, is that basically you have these numbers like 1, 1, 0, 0, 1, 1, say that that's x. And you want to add 3 numbers to that. Well, basically, it's just saying, well, just play around with these zeros, because these ones need to stay the same. You can't alter those. So just basically just count upwards within the zeros. So I would say, take that, and then I would say, okay, well, just like we have 3 zeros right here, so we'll count upwards with them. And so on. And basically, you just place those within the zeros right here. So, for example, the first one, 0, 0, 1, would be 0, 1, 1, 0, 1, 1, 1. Okay? So, how do we do that? That I was not my best at. I did unset bit locations, and what I did was, this was originally a helper function. I just went through all of the bits in x, and I just counted I just held on to where they were zeros. Because then I could take what would be the last number in the sequence. Because essentially, if you have an array of size 5, well, the first number is x, and that's the 0 index, and the length is n. So you want to solve for n minus 1, because that will be the last number in the index. Because the 0 index is x, and then 1 is x plus 1, and 2 is x plus 2. And so on. So we want to solve for that final number of n minus 1. So we're basically taking the binary string of n minus 1. So like x is 0 index. 1 index is x merge 1. Where merging is the act of replacing the unset bits with a number. Okay? So merging 1100 with 1 would be 1101. You get it. I'm repeating myself. So we're just basically solving for the last number in the array, which is n minus 1. So the final number is n minus 1. So we're just basically replacing all of the zeros with the string of n minus 1. And so we do that by holding on to the unset bit locations. And we calculate whether or not the next bit that we're adding is a 1 or a 0. To do that, I am just basically isolating. I'm checking to see if a bit at a certain location is a 1 or 0. So if we have 4, we would check. So 1 bit shift 2 gives you 4. So it's complicated. Basically, this is bit masking. So what's a quick way of saying, hey, is there a bit at the third location? Well, you could just AND it with 1 shifted twice. And so this says, hey, does this and this equal anything? And it says no, because the AND of those two is 0, meaning there's not a bit at that location. So using that logic, I'm basically able to say, hey, go through all the bits that are there, and then just OR them, or just basically add them to the bit string, shifted by the unset bit locations. So we're going through, we say, okay, well, is there a bit at the first location? Yes. Okay, well, where's the first spot where we can slide that into? The third location. Okay, so put it there. I am struggling to explain this one. I hope that vaguely makes sense. It's not the fastest. There's some better solutions. This one's pretty elegant, and I am too tired to try to understand it. But mine worked. It was definitely variable with the submission times, as you can see. Like 7 milliseconds, 7 milliseconds, 11 milliseconds, so on. But it works, and with a problem like this, I'm just happy to get it done. Thank you.